Good morning, students. In the last class, we have discussed the heterogeneous and homogeneous equilibria. That is, in the homogeneous equilibria, we have given a relation Kp is equal to Kc into Rt raised to delta n, and when whatever the units of Kp and Kc. In this class, I will give the next part, that is applications of equilibrium constant. Applications of equilibrium constant. Before going for the application of equilibrium constant, let us discuss the important characteristics of equilibrium constant. Okay. In the last class, we have given the units of equilibrium constant. Now, characteristics of important can be asked in 3 marks. Characteristics of equilibrium constant. Characteristics of equilibrium constant. First one, the value of equilibrium constant. The value of equilibrium constant of a given reaction. Value of equilibrium constant of a given reaction at a given temperature or is constant or is having unique value. That is, for every reaction the value will be constant at a constant temperature and pressure. If either of temperature or pressure or both, if either of temperature or pressure or both are changed, then value of Kc also changes. Value of Kc also changes. Second one, the value of K does not depend on initial concentration of reactants and products, pressure or volume of vessel used. So, first point, the value of equilibrium constant of a given reaction is constant, that is unique value at constant temperature and pressure. If either of temperature or pressure or both are changed, value of Kc also changes. Now, next is the value of K does not depend on initial concentration of R and P, or pressure or volume of the vessel. Third one, the magnitude of Kc indicates extent and direction of the reaction. So this we will study in the applications of equilibrium constant. Then fourth one, for a reversible reaction, equilibrium constant for the reverse reaction. For a reversible reaction, equilibrium constant for the reverse reaction is inverse or reciprocal of equilibrium constant for forward reaction, that we have studied in the last but one, or that is day before last class. Now, next point, equilibrium constant is applicable. Equilibrium constant is applicable when concentration of reactants and products are or have attained equilibrium state. Then sixth point, the equilibrium constant equilibrium constant for a reaction K is related to equilibrium constant K of a reaction or for a reaction is related to K of corresponding reaction whose balanced equation is or can be obtained by multiplying or dividing by small integer. Okay, these are the important characteristics of equilibrium constant. Okay, all are important. Go through it and make a note of this. Next is applications of equilibrium constant. Next part of the topic is applications of equilibrium constant. Applications of equilibrium constant. In this, equilibrium constants can be used to study to predict extent of the reaction. Second one, to predict direction of the reaction. And third one, to calculate equilibrium concentration of reaction mixture. Okay, so here equilibrium constant can be used to predict extent of the reaction. Then it is used to predict direction of the reaction. Then third one, used to calculate equilibrium concentrations of reaction mixtures. First one, prediction of extent of the reaction. So extent of the reaction ಅಂತಂದ್ರೆ ಕೊಟ್ಟಿರೋ ಡೈರೆಕ್ಷನ್ ನಲ್ಲಿ ರಿಯಾಕ್ಷನ್ ಎಷ್ಟು ದೂರದವರೆಗೆ ಹೋಗಿದೆ ಅನ್ನುವಂತ ಮಾಹಿತಿಯನ್ನು, ಅಂದ್ರೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಂಡಿದೆ ಅನ್ನೋ ಮಾಹಿತಿ ಅಲ್ಲ, ರಿಯಾಕ್ಷನ್ ಈ ಡೈರೆಕ್ಷನ್ ನಲ್ಲಿ, ಅಂದ್ರೆ ನಾನೀಗ ಯಾವುದೋ ಒಂದು ಡೈರೆಕ್ಷನ್ ಹೇಳ್ತೇನೆ, ಆ ಡೈರೆಕ್ಷನ್ ನಲ್ಲಿ ಎಷ್ಟು ದೂರದವರೆಗೆ ನಮ್ಮ ರಿಯಾಕ್ಷನ್ ಹೋಗಿದೆ ಅನ್ನುವಂತ ಕ್ವಾಂಟಿಟಿಯನ್ನ ನಾವು ಎಕ್ಸ್ಟೆಂಟ್ ಆಫ್ ದ ರಿಯಾಕ್ಷನ್ ಅಂತ ಐಡೆಂಟಿಫೈ ಮಾಡ್ತೀವಿ. ಸೊ ಆಸ್ equilibrium constant is the relation, that is K is equal to concentration of products divided by concentration of reactants. When K is larger or K is higher value, then concentration of products is more than concentration of reactants. So that we can say all the reactants are consumed or all the reactants are converted to products, or reaction will go to completion. Okay, when K is smaller, concentration of reactants is greater than concentration of product. So in this case, the reaction hardly occurs. So that based on the values of Kc, we can decide the extent of the reaction. Based on values of K, extent of the reaction can be given. Okay, so like this, first one, when Kc very greater than 10 raised to 3, when Kc very greater than 10 raised to 3, here we say that concentration of products are greater than concentration of reactants, or products predominate as Kc is very large. Okay, so that reaction proceeds to completion. completion. Almost, we say almost all reactants are converted to products. Okay, so here let us take one or two examples in this case, that is Kc greater than 10 raised to 3. So how the reaction will be occurring? For that, first one, reaction between H2 plus O2 at 500 Kelvin, that is formation of H2O liquid at 500 Kelvin. Kc is equal to 2.4 into 10 raised to 47. So it is Kc is very large, so that we can have the formation of products, that is liquid water in the large quantity. Second example, H2 gaseous plus Cl2 gaseous reversibly giving rise to 2HCl gaseous at 300 Kelvin. Kc is equal to 4.0 into 10 raised to 31. So that we can have the products as HCl in the major quantity. Third reaction, H2 gaseous plus Br2 gaseous giving rise to 2HBr gaseous at a constant of 554 into 10 raised to 18. So that we can form HBr, that is hydrogen bromide in the large quantity. Second case number 2, when Kc is in between, Kc is in a range of 10 raised to minus 3 to 10 raised to plus 3, so that concentration of reactants as well as concentration of products are present in reaction mixture. So when the value of Kc is in between 10 raised to minus 3 to plus 3, concentration of reactants as well as concentration of products are present in the reaction mixture, so that we say Kc is neither too small nor too large, so that equilibrium mixture contain appreciable amounts of equilibrium mixture contain appreciable concentration of reactant and product. So here example under this class will be H2 plus I2 reversibly giving rise to 2HI at 700 Kelvin. Kc is equal to 57. So here reactants and products will be present at a stage of equilibrium. Now second example in this, N2O4 gaseous giving rise to 2NO2 gaseous. So in this reaction at 25 degrees, Kc is equal to 4.64 into 10 raised to minus 3. Here also we can say that appreciable amount of reactants and products are present in the reaction mixture. That is, equilibrium state will have products as well as reactants in the reaction mixture. Okay. Now next third case, that is third case, when Kc is less than 10 raised to minus 3, when Kc is less than 10 raised to minus 3, we can say that reaction hardly occurs. Reaction hardly occurs. The generalizations are illustrated by, the generalizations can be given by, so with the help of arrow mark. So here starting of the arrow mark and ending of the arrow mark. So this arrow mark, here it is negligible Kc values. So here in the range 10 raised to minus 3 to 10 raised to plus 3. So that at this stage extremely large Kc values. So when the values are negligible, we say that reaction hardly occurs. Okay. Then both reactants and products are present at equilibrium. Then reaction, when extremely large, reaction proceeds to completion. So this is the generalization given for extent of the reaction, how to predict the extent of the reaction based on the values of Kc. If Kc is very greater than 10 raised to 3, we can say that reaction proceeds to completion. Then if Kc values are in between 10 raised to minus 3 to plus 3, then both reactants and products are present in a stage of equilibrium. And when the value of Kc is very less than 10 raised to minus 3, that is negligible values, reaction hardly occurs. So here your extent of the reaction is completing. Second one, prediction of direction of the reaction. Prediction of direction of the reaction. Prediction of direction of the reaction. So in order to predict direction of the reaction, we require or we define a new quantity, a quantity called reaction quotient. Reaction quotient, which is represented by the letter Q, so that based on the at any time, so that we define a quantity reaction quotient, so that based on the reaction quotient we are giving the directions for the reaction. Okay, so here I will first define the quantity reaction quotient, then I will give you how to predict the direction of the reaction using reaction quotient. Okay, so here reaction quotient QP, QC or QP is the ratio of product of molar concentrations of or partial pressures, molar concentrations or partial pressures of reaction products to that of reactants at any stage. So we can define the same in the, we have defined the equilibrium constant. In the same way we are defining the term reaction quotient. Okay, but equilibrium constant is defined at the stage of equilibrium, and reaction quotient is the meaning of the definition at any stage other than equilibrium. Now here reaction quotient in terms of concentration, that is also called as concentration quotient can be defined as QC is equal to CC raised to C, CD raised to D divided by CA raised to A, CB raised to B at any time or at any stage. Okay. Similarly, reaction quotient in terms of partial pressure can be represented by, it is called as pressure quotient, and this is defined as pressure quotient QP is equal to PC raised to C, PD raised to D divided by PA raised to A into PB raised to B at any stage. Okay, so here also we can write the relation QP is equal to QC RT raised to delta N. In the similar way, we have given a relation between Kp and Kc. We can give a relation in between reaction quotient, that is concentration quotient, and pressure quotient. Okay. Now how to define or how to compare the direction of the reaction? Let us see how to just based on reaction quotient, how to give the definition or direction of the reaction. Let us discuss in this part. Okay. So by comparing values of Q and K, reaction constant with respect to equilibrium constant, direction of the reaction can be predicted. By comparing Q and K, direction of the reaction can be predicted. Okay, so here make 3 columns: condition, then observation, lastly conclusion. Condition, observation, and conclusion. So in the condition, first condition is if QC is equal to KC, or we say QP is equal to KP, so that observation is concentrations of reactants and products are equal to those at equilibrium. Reaction concentration of reactants and products are equal to those at equilibrium. So conclusion is reaction is at equilibrium, or we say no net reaction occurs. Okay, no net reaction occurs. Second one, if Q greater than K, that is concentration of products is greater than concentration of reactants. So here I will write in this observation, products are present, concentration of products is greater than concentration of reactants, so that net reverse reaction occurs. Reverse reaction in the sense product to reactant, and reaction proceeds to left in the direction of reactants. Reaction proceeds to left in the direction of reactants. That is, direction of the reaction is right to left. Okay, this is the prediction for Q greater than K. Third one, if Q less than K, then concentration of reactants are greater than concentration of products, so that net forward reaction occurs. Okay, so that R giving rise to P is the reaction, and reaction proceeds to right in the direction of products, or direction will be from left to right. Okay, this is the after this direction of reaction, that is based on the values of K, that is if K is equal to Q, then the reaction is at equilibrium. Q get greater than K, then the net reverse reaction occurs, that is P to R, or the direction of the reaction will be right to left. And if Q less than K, then net forward reaction occurs, so that the direction is from left to right. Now I will solve one or two problems related to the direction of the reaction. Problems. First one, for a gaseous reaction, H2 plus I2 reversibly giving rise to 2HI at Kc is equal to 57.0 at 700 Kelvin, and molar concentration of species at some arbitrary time R. Concentration of H2 at time t is equal to 0.10 moles. Concentration of I2 is equal to at time t is equal to 0.2 moles, and concentration of HI at time t is equal to 0.4 moles. Okay. So what is the direction of the reaction? So here, in order to solve this problem, what we have to do here? So first write given solution. First write the given things. Given H2 gaseous plus I2 gaseous reversibly giving rise to 2HI gaseous. So that and species concentrations are given. H2 at concentration T is equal to 0.1 mole, I2 at concentration T is equal to 0.2 moles, and HI at concentration T is equal to 0.4 moles. So now for this equation write the reaction quotient QC, that is QC is equal to concentration of HI raised to 2 divided by H2 into I2. So that is equal to HI is 0.4 raised to 2 divided by 0.1 into 0.2, or it is 0.16 divided by 0.02, or equal to 8. Okay. Now compare the values of QC and KC. QC is 8 and KC is 57. So that KC is greater than QC, or we will write QC is less than K. So that what is the direction of the reaction as per this time column? This net forward reaction occurs. Net forward reaction occurs, that is formation of HR. Okay. So I will solve another problem related to this direction of reaction. I will solve another problem related to direction of reaction. Second problem. The value of Kc for a reaction. Second problem. The value of Kc for a reaction. The value of Kc for a reaction 2A giving rise to B plus C is 2 into 10 raised to minus 3 at a given time. Composition of reaction mixture is A is equal to B is equal to C is equal to 3 into 10 raised to minus 4 moles per liter. In which direction will the reaction proceed? Okay. So here the problem is same manner. So that first write the given things. Given given solution Kc is equal to 2 into 10 raised to minus 3, time is given, and reaction is 2A giving rise to B plus C. Okay, so that we are given as A is equal to B is equal to C is equal to 3 into 10 raised to minus 4 moles per liter. So for this reaction, write the reaction quotient QC is equal to concentration of B into concentration of C divided by concentration of A raised to 2 at the time T. So here at the time T. Okay. So write the concentration. B is 3 into 10 raised to minus 4 square divided by 3 into 10 raised to minus 4 square, that is equal to 1. Now compare the values of QC and Kc. QC is 1, Kc is 2 into 10 raised to minus 3, so that QC is greater than Kc. Therefore, net reverse reaction occurs, that is formation of A. Okay. Now next concept is, so I am leaving the equilibrium, calculating of equilibrium concentration. So next one is relationship between equilibrium constant and free energy change of the reaction. Next subheading, relationship between equilibrium constant, reaction quotient, and gives free energy change. Okay, so this is reaction quotient, this is gives free energy change. So as per the thermodynamics, which topic you will be studying later, in that one concept will be there. So free energy of the reaction is given by delta G naught is equal to minus RT ln Kp or Kc. Okay, so here equilibrium constant can be related to free energy change of the reaction by the relation delta G naught is equal to minus RT ln K. Here delta G is negative, so that Kp is positive, so that we say that process is spontaneous. Spontaneous means the process is going to take place of its own, okay, without any force. Now if delta G is positive, then Kp is equal to negative, then we say that process is non-spontaneous at a given temperature. Okay, so now by the help of thermodynamics, we can give the relation between equilibrium constant Q and delta G by the relation delta G is equal to delta G naught plus RT ln Q. This is the relation which gives change in free energy, then standard free energy change and reaction quotient at a given temperature. Here delta G is the free energy change. Delta G is the free energy change of the reaction. Then delta G naught is the standard free energy change of the reaction. Similarly, Q is the reaction quotient. Okay. Now apply the condition of equilibrium, that is at equilibrium. What will be the condition? We say that Q is equal to Kc. Q is equal to Qc or Qc is equal to Kc, and delta G is equal to 0, so that we get the equation 0 is equal to delta G naught plus RT ln Kc, or delta G naught is equal to minus RT ln Kc. This is the relation to write the equilibrium constant and free energy change of the reaction. Okay. So in this equation, so what will be the terms explaining? If delta G is negative, that is process of spontaneity, we tell that if delta G is negative, then we say that process is spontaneous at a given temperature, then Kp is equal to positive, and if delta G naught is equal to positive, then we say that Kp is equal to negative and the process will be non-spontaneous. Like this, we can have the reaction, that is relation between standard free energy change and that gives a free energy change of the reaction and equilibrium constant, and the relation between delta G and K. Okay. So next part I will continue in the next class. Okay. Thank you.